In video 2 of module 6, we're going to continue our discussion of viscous flow in ducts, and we're going to continue with introducing the head loss or the friction factor that we would see in a pipe. So typically when we have a pipe flow, we try to approach the problem using a control volume analysis. And the reason why is because it's usually simpler to solve. So we like to use a control volume analysis to try and solve our problem. And through this, we're going to be able to come up with a term for our friction and our head of friction, and another term called the friction factor, the Darcy friction factor, which will allow us to relate the friction in a pipe based on Reynolds number, based on the duct shape as well. So let's say that we have a constant pipe area, just to start with an assumption. So we have a constant pipe area, and we're also told that the flow is incompressible. Okay, we're going to make that assumption in pipe flow for most of our problems. And what we can say is if we have a constant pipe area and we're looking at a control volume analysis, so let's say we have a pipe like this, okay, and we have, let's say, point 1 or plane 1 is here, and then plane 2 is here, which would be the entrance and the exit. We can have a control volume analysis on this control volume right here. And we can say that if we have flow into here and out of here, we can say that the mass flow rate of 1 is equal to the mass flow rate of 2 if we have steady flow. Okay, and since it's incompressible, we can also say that Q1 is equal to Q2. Okay, the volume flow rate is equal to the volume flow rate at the exit. And in addition to this, we can also say that velocity 1 is equal to velocity 2 because the areas are the same. Okay, so if we assume that the area coming in, A1 is equal to A2, we can say that V1 is equal to V2. Okay, just a very simple flow analysis through the pipe. Now, the one thing we have to look at is, let's take this in terms of our energy equation. So let's look at a steady flow analysis, and let's look at the energy equation for this steady flow. And if we look at the energy equation, we know that the energy equation has the term for with pressure, velocity, and height is equal to the term with pressure, velocity, and height plus the head of friction minus the head of the pump plus the head of a turbine. Okay, in this case, we don't have a turbine or a pump, so the equation would simplify to the following. We would have P1 over rho g plus alpha v squared over 2g plus z, and that would be at 1. Okay, so I'm not even going to put P1, I'm just going to leave it as P, but they're all sub 1, is equal to P over rho g at 2 plus alpha v squared over 2g plus z, all at 0.2, plus our head due to friction. So if we have frictionless flow, we wouldn't have any friction, but usually in a pipe, we will have some friction flow. So remember, I have included alpha here. So remember, alpha is a kinetic energy correction factor. And if you remember correctly, the kinetic energy correction factor plays a role when the flow is laminar. It doesn't really play a role when the flow is turbulent. I mean, it does change the value a little bit, but when the flow is laminar, alpha is usually equal to 2. So it's going to be very important to have that term in our initial equation. Now, in this case, in the case of a simple pipe flow going from 1 to 2, okay, if we just have 1 to 2, so plane 1 and plane 2 with velocity going in like this, we know that velocity 1 is equal to velocity 2. And since velocity 1 is equal to velocity 2, we can say that alpha 1 is equal to alpha 2. So we can say that in the above equation, the velocity term would essentially cancel. Okay, now our height term we're going to keep for now just in case we have different heights. We're not given any information on heights, and if the tube is inclined to a certain angle, then we might have different heights. And we might also have different pressures at 1 and 2 driving the flow. So we come out with an equation if we rearrange for HF. So we can come up with an equation for HF. So HF would be equal to, following some rearranging, HF would be equal to Z1 minus Z2. So that would be our height terms. And this could be 0 if they're on a horizontal plane, for example, plus P1 over rho G minus P2 over rho G. And remember, rho is constant, so rho stays the same. So we have an equation that says this is equal to delta Z plus delta P over rho G, okay, in its most general form. And this is our equation essentially for HF. We can say HF is related in a pipe flow directly to the change in height plus a change in pressure over rho G. Okay, we can also write this in words as the pipe head loss equals the sum of pressure and gravity head. Okay, and so we're assuming that our pipe can go in any direction at this point. Okay, we don't know if our pipe is going to be flat or not, so that's why we have these different terms. We also don't know the pressure difference. Okay, so now I'm going to copy over this example of a pipe at a certain angle just to develop the most complex form of the equation, and then we'll see how that simplifies later on. So here we have an inclined pipe, and we're given this inclined pipe, and we see that we have P1 is equal to P2 plus delta P. We also have a velocity going down. We see that there's a velocity profile as a function of R here. We see that there's a certain velocity profile, okay? And we're also told that there's a certain angle with the horizontal, which is shown right here, which is phi. And so what we're going to do with this is, now that we've developed a certain equation for HF, how about we also look at the momentum equation for this, or the force equation for this. Okay, so let's do a linear momentum analysis of this system. And if we do a linear momentum analysis, we have that the sum of the forces in x, and we're going to do it in the x direction, is equal to m dot times v2 minus v1. Okay, and we see that the x direction is defined as the direction here. So it's defined as this direction here. You can also see it here, gx. But the gravity is not aligned with gx, so it's not in, the gravity is not in the z or the y direction. Okay, so we see that there is a different angle between x and gravity than usual. Okay, so we're gonna have to take that into account. Okay, just letting you know. All right, so we have linear momentum. We know that linear momentum is equal to m dot times v2 minus v1. Okay, the mass flow rate is constant. We have a constant area pipe, and it's just going to be multiplied by v2 at the exit minus v1 at the entrance. Now, as for the sum of forces in x, we can come up with a sum of forces in x with the terms explained in the diagram. So we see that the total radius of our system is r. We have it right here. So if the radius goes all the way to the top, this is equal to r. Okay? And through this, we're going to be able to find our sum of forces in x. So the first thing we can do is find the force in the x direction due to pressure. Now, we know that due to pressure, P1 is equal to P2 times delta P. So we know that we can use our gauge pressure expression for this system. So our gauge pressure expression for the sum of forces in x is delta P times the area, pi r squared. Okay, so the delta P is essentially our gauge pressure, our difference between 1 and 2, and we're going to use that as our term for the pressure due to the force due to pressure. Now, for the other terms, we also have a term that creates a force within our system that is related to gravity. And that term is rho g times the area, pi r squared, multiplied by the length in the x direction. Okay, and the length in the x direction is L sine phi. Okay, so it's going to be L times sine of phi. And in addition to this term, we're then going to get our force due to shear, once again in the x direction, is going to be equal to negative tau. Okay, our force due to tau is negative. Okay, we see it here. Our tau is going towards the left side, it's going up. Okay, so we have minus tau of w. Okay, that's our tau w is our tau for the wall, multiplied by 2 pi r, which is your circumference of the wall, times the length. So that's essentially that's the area on which the shear stress is acting upon. And we have that this is equal to m dot times v2 minus v1. And we also have that this is actually equal to 0. Why is it equal to 0? Well, because we're told, and we're not really told because this is not a question but more of a derivation, but we assume that the tube is not moving. If the tube is not moving, the acceleration is 0, therefore we have 0 for our sum of the forces in x. So the forces are balanced in the x direction, essentially. Okay, so if we rearrange this equation, we can actually get our delta P and delta Z terms on one side is equal to something else, essentially. So what we're going to do is we're going to take all of this equation and we're going to try and rearrange it so that it makes some sort of sense in terms of it being equal to 0. Okay, so how do we do this? Well, we're going to say that we can cancel some things out. So if we keep this part of the equation and this part of the equation, so we don't really care about m dot v2 minus v1, but we know that v2 has to be equal to v1 in order to be equal to 0. So we're just going to use that part of the equation, and we're going to write it in terms of tau w. So we're going to say that 2 tau w over rho g. Okay, so 2 tau w over rho g times L over R is now equal to, and we'll keep this on the left side, delta P over rho g plus R delta Z. Okay, and we can go further with this and say that this is also equal to 4 tau w times over rho g, times L over D. So we were able to cancel out some terms in our equation above, so we can cancel out, I'll do it in green, we can cancel out our pi terms. Okay, we can also cancel out some, if we divide everything by rho g, we can have rho g on the bottom. Okay, so our rho g would be canceled from the middle term and would go under tau w. So this is just to get the format right. And then L sine of phi is essentially our delta z. Okay, so we're left with, so essentially in green once again, this term goes to here, this term goes to here, and then this term came to the other side of our equation. We also divided everything by r squared. So we divided everything by r squared so that we would get the L over r on the bottom. Okay, so this is just mathematics, but hopefully you follow by just rearranging, not step by step, but just in a big one step. Now, the reason we rearranged our equation like this is to get this left side term, this term right here, we wanted to get it into this format. Why did we want to get it into this format? Because this, if we remember our energy equation for a pipe, and for this pipe it would work as well, our energy equation says that this is equal to HF. So we can say that HF is equal to delta P over rho G plus delta Z, but is also equal to, in terms of shear stress, 4 tau W over rho G L over D, if we use diameter, or we can also use it in terms of radius, which it would be 2 tau W over rho G times L over R if you're using the radius. So we have this equation essentially for our HF. Now, because we have this equation for HF, we can also write, and just to clarify here, so the L sine theta, or sine phi, sorry, is equal to delta Z, okay? It's a change in height. Okay, so we have an expression for HF. Now, in 1850, an engineer called Weissbach came up with the idea that the friction and the friction head was actually proportional to different terms by doing some experimental testing. So he found out that HF, or H of friction, okay, can be uppercase or lowercase f, let's keep it as lowercase for now, is directly proportional to L over D, the length over the diameter, and also velocity squared. And from this, he came to an equation that essentially said that HF is equal to a factor F multiplied by L over D multiplied by V squared over 2G. So he took the above equation and this left side of the above equation and decided to do some experiments and found out that HF was directly related to L over D and to velocity, and he was able to rearrange HF into force times L over D times, sorry, not force, but a factor times L over D times V squared over 2G. And this F here is called the Darcy friction factor. So F is equal to the Darcy friction factor. And this friction factor was found out to be a function of Reynolds, of E over D, and of duct shape. And this E here, okay, so it's an E, it's a Greek E essentially, and this E is the wall roughness height. Okay, so this E over D is actually the wall roughness height. So depending on the wall roughness height and the height of the roughness in the wall, you would have a different friction factor. So obviously the smoother the wall, the better, and the less smooth the wall, the more friction you would get. So he realized that this was a function of these three terms. And for circular ducts, he then concluded that F was equal to 8 tau W over rho times velocity squared. And this is for circular ducts. Okay, so we now have a new term for our head due to friction, and we can find our head due to friction independently of our pressure and our height. We can find it by the length over d and the velocity squared now, because we found out that it was a function of those. But we need to know the Darcy friction factor. And the Darcy friction factor is itself a function of Reynolds, a function of the wall roughness, and a function of the duct shape. Now, moving further, if you assume that you have a circular duct, you can also say that the Darcy friction factor is 8 times tau of the wall over rho v squared. Okay, so now let's look at an example of fully developed laminar flow. And now that we have a term for friction and all these different things, we can start determining what our fully developed laminar flow is going to give us in terms of our analysis. Now, for this solution, for fully developed laminar flow, we had to use our methodology from module 4, from chapter 4 in your book, to determine how the flow would work in fully developed laminar in its detail. Okay, so not just looking at a control volume approach, but actually looking at a more precise approach. And for fully developed laminar flow, an experimentalist called Poiseuille. So Poiseuille named this flow after himself. And what Poiseuille flow for a circular duct? And what Poiseuille did is he actually developed a bunch of different equations to developed a bunch of equations for us to solve flow in a round pipe which has a diameter d and a radius r. And in your book in section 4.10, so going back to chapter 4, in section 4.10 there's a full derivation of how these terms are found from your differential methods directly. What we're going to do here is we're actually going to summarize these equations. So I'm going to bring in another figure from your handout with all the summary of the equations that are developed, and we'll look at a few of the highlights of them. Okay, and for any laminar flow, you could use this. For any fully developed laminar flow in a duct, you could use these equations directly. However, you can also work directly from your initial linear momentum equation and the fact that you now have a friction factor to solve for the problem. But we do need to have one information extra. So if we look at fully developed laminar flow, we see that our first term that was derived is U is equal to U max over 1 minus R squared over R squared. Okay, and what this term is essentially to develop this velocity profile that we see here. Okay, it's trying to find a velocity at any point on this curve essentially. So if we have pipe flow going sideways, let's say, and we have a velocity profile that looks like this for fully developed flow, which is what it looks like, we can actually find the velocity. We can find the velocity at any point within that radius, okay, where little r is the amount you're moving away from the center and big R is the full radius, you can actually find your u. So if you know your maximum velocity at the center, okay, this would be your u max, you can then find out any u that's along the profile as you get closer and closer to the wall. Okay, that's the first thing. And what we can say is, based on that, there's a bunch of derivations that you can do to solve for the problem in terms of radius, in terms of volume flow rate, and in terms of tau w. And you also find that there's a certain equation for HF in terms of velocity and in terms of Q. So remember that your book doesn't use the V with the bar through for velocity. So just make sure that you adjust to that when you're taking your notes and comparing with my notes, for example. So all these formulas can be used, are valid for Reynolds is less than or equal to 2,300. So if we have Reynolds of less than 2,300, we can use all these formulas. Okay, so we can find this term u here is also called our local velocity. Okay, so what can we do with this? Well, with this, what was actually figured out is that if you know the wall shear stress, you can say that your friction factor, okay, and once again, this is not going to be derived, but your friction factor for a laminar flow is going to be equal to 8 tau wall for laminar flow divided by rho v squared. And we see that tau w for laminar flow is given right here, and we see that it's equal to 8 mu V over D. So we can actually plug that in. So we can say that F laminar is equal to 8 times 8 mu V over D over rho V squared. Okay, so now we're looking specifically at laminar flow. Before we were looking at a general equation for laminar and turbulent flow. Now we're looking only at laminar flow and looking at this specific type of flow called Poiseuille flow. So moving forward from that, we can now simplify and say that this is equal to 64 over rho V D over mu. Okay, so we have 64 over rho V D over mu. If you do the math, it'll work out. And finally, this term at the bottom here is actually Reynolds. So we get that this is equal to 64 over Reynolds D. So we can say, essentially, that our friction factor, our Darcy friction factor for laminar flow is related directly with Reynolds number, inversely proportional to Reynolds number. So that means that if Reynolds increases, we have less of a friction factor. And we have less friction too, because remember that our friction, HF, is equal to F times L over D times V squared over 2G. So we can use this for HF if we given L over D and V squared, and then plug in our F into here for laminar flow, for example. Or we can use this equation, HF is equal to the one that's shown right here. HF is equal to 128 mu LQ over pi rho G D to the fourth. But in that case, you would need to know your volume flow rate or your velocity. Just two different ways of doing it. Either way is fine. This is more of a specific solution, whereas the general equation will let you do it for any general equation. So let's try and do an example problem and see if we can solve an example problem for laminar. So if we know we have a laminar flow, we can simplify our problem and directly say, let's use all the equations in this sheet right here. It makes it a lot easier. It's already developed for us so that it's already simplified so that everything is taken care of. Okay, so let's do an example problem and see how that goes. So we're going to do example 6.3 in your book. Let me copy over the question. And example 6.3 says that we have an oil with a density of 900 kilograms per meters cubed and V of 0.0002 meters squared per second flows upwards through an incline pipe as shown in figure E6.3. The pressure and elevation are known to be The pressure and elevation are known at sections 1 and 2, 10 meters apart, assuming steady laminar flow. Verify that the flow is up, and then compute HF between 1 and 2, and finally compute Q, V, and Reynolds D. So this first V here shouldn't be shown as a V, okay? It should actually be our V for our kinematic viscosity. So this is kinematic viscosity. And in the printed copy of your book, you would have it as the Greek symbol nu. So you would have it as the Greek symbol nu, but for some reason in the online version of the book, you don't have it as nu. It's just a typo essentially. Okay, so that can be a little challenging at the start because it's meters squared per second, which doesn't really make sense, but hopefully that solves the problem. Okay, so we're asked to verify if the flow is up if we assume laminar flow. So first of all, we're going to assume laminar flow. And if we assume laminar flow, we can use the equations that we just copied over for laminar flow. Now, how do we solve part A, verify that the flow is up. How do we verify that the flow is up? Well, we know that flow goes in the direction of pressure going down. Okay, so if pressure is high on one side and low on the other side, then pressure goes in the direction of pressure loss, essentially. So we can write that flow goes in direction of pressure loss. And since we now have to take into account our friction, because we're looking at viscous flow in ducts and not inviscid flow in ducts, where we would just have Bernoulli's equation, we now have to come up with, so we have a straight pipe, and we now have to come up with an equation for this. So the equation we're going to use is our energy equation. So our energy equation says that P1 over rho g plus alpha V1 squared over 2g plus Z1 is equal to P2 over rho g plus alpha 2, let me put alpha 1 there, so alpha 2 V2 squared over 2g plus Z2. Now, in our flow, we know that the velocities are going to cancel. We have a constant q throughout the area, and the area is not changing, so the velocity has to stay the same. We have steady flow. So that means that our velocity is not changing. So this term goes to 0, and this term goes to 0. Okay? Now, in our energy equation, we have the h of friction term added to the system. So we have h of friction, or hf. Now, we are left with P1 over rho g plus Z1 is equal to P2 over rho g plus Z2 plus HF. So how are we going to determine whether or not our system flowing from down to up or from up to down? Well, we have to figure out our total pressure at point 1 and our total pressure at point 2. So it's very important. This term here, P1 and P2, these terms are not the total pressure at that level. The total pressure at that level is actually the whole term. Remember that this is the total pressure. If you remember our analysis of hydraulic grade lines and energy grade lines, those are essentially what we're looking for here. So this is our total pressure of our system at 1 and our system at 2. And H friction is basically the difference between the two pressures. So what we're going to have to do is we're going to have to figure out our hydraulic pressure at point 1 and our hydraulic pressure at point 2, or our total pressure essentially at point 1 and our total pressure at point 2. So total pressure at 1 is equal to Z1 plus P1 over rho g. So let's look for information. So we can say Z1 is equal to 0. It says on our problem here, it says Z1 is equal to 0. We also know that pressure 1 is 350,000 pascals. So we can just plug in the values and get a value for the grade line. So we can say that this is equal to 0 plus our 350,000 divided by 900, which is our density, multiplied by 9.81. And we get that this is equal to 39.65 meters. Now at 2, we have Z2 is equal to 10 times sine of 40, okay? And from that, we can have Z2 plus, so Z2 is going to be 6.43 plus, now we have at 2, we have 250,000, so it's going to be plus 250,000 divided by 900 times 9.81. And we get a value of 34.75 meters. Okay, so moving forward from that, we now have our two hydraulic grade lines. So we have our total pressure at 1 and our total pressure at 2. We see that the pressure at 1, so 1, is greater than 2. So we can say that therefore flow is going up. Okay? It's very important to take into account the height in that problem. If you had different velocities, it's also very important to take the velocity into account. So you would take all three terms into account, okay, in order to tell us if the flow is going the right way, okay? In this case, since we only have height, the total pressure head is kind of the same thing as the total hydraulic pressure head. So just a gravity head, essentially. But in some cases where you have different velocities, it would be your whole term. Okay, so part B of your question. Part B of the question asks for compute HF between 1 and 2. Well, we already have the total pressure at 1 and the total pressure at 2, so HF is just going to be the difference between the two. So the head loss, HF, is going to be equal to 39.65 minus 34.75. And we get that this is equal to 4.9 meters. So that's our total head loss. Part C asks us to find our Q. So since our Q is constant, we can use any velocity or any area. So we have Q is equal to A times V. Now, A times V is, we would have to know a bunch of information to be able to find A times V. Now, if we look at our laminar flow formulas, we can actually find Q. So from our laminar formulas, we actually have a term for Q. We can say that Q is equal to the following. We have that Q is equal to pi r squared V, or pi r to the fourth times delta P plus rho GZ over L over 8 mu, and we can work it out that way. Now we can also use, if we want to, we can also use the following, so we can use that equation if we want to, and we do have delta P, we do have all the values, okay? The other equation that we can use, and let me actually copy over this here so that we have it in our actual question and it's not populated with other things. So we can either use this equation to find Q. So where we have all the values, we just have to plug in all the values, delta P plus rho GZ over L. We have all those values, we can plug them in. Now the other thing we can use, since we have found HF, we can actually use this equation right here. So we can use this equation and rearrange it if we want to. So in order to simplify our lives, there's a little bit less terms on this side. I mean, it's pretty much the same thing, but you can use either or because you've already found the head loss. So you can say from the head loss equation that Q, and let me write it in white, Q would be equal to pi times rho GD to the fourth over 128 mu L. Okay, the other equation you can use is this one, but we're not going to use it for this problem because we think it's easier to use the second equation. I believe it's easier to use the second equation. Plus, it makes it easy because you're always using the same equation. Okay, so it makes it easier in that case. And we have that Q is therefore equal to, so is equal to 0.0076 meters cubed per second. And for this mu value, since we're given our kinematic viscosity, we can just say that mu is equal to density times the kinematic viscosity. Okay, so very important that you have to plug in our mu is equal to density times kinematic viscosity, which would be equal to 900 multiplied by 0.0002, which would be equal to 0.18. Okay, that's the only value that's not directly in your question. The rest you can find from your question prompt. Okay, now the great thing with this second equation that we just used is that we can actually use this for Q, but we can also use it for velocity if we're given velocity as opposed to Q. Now that we have our Q, we can actually find velocity very easily. So for part D, we're asked to find velocity. So for part D, we just say that velocity is equal to Q over area. And velocity is equal to Q over pi times r squared. Okay, we could plug in to this equation again, but it is easier to just use the definition of velocity is equal to Q over A and just plug that in. So we have that Q over pi r squared is going to be equal to 2.7 meters per second. And finally, in part E, which is probably the most interesting part of the problem, it says Reynolds number. Find the Reynolds number. Is the flow really laminar? So let's look at the Reynolds number for our flow, and let's look if it actually makes sense to have done this whole analysis as laminar. So Reynolds, if you remember, is equal to rho v d over mu, or velocity times diameter over our kinematic viscosity. And if you plug in the values, you get 810. Remember that Reynolds is dimensionless, so there's no dimensions. Since Reynolds is 810, it's lower than 2,300, so we can say it's laminar. So we can say that Reynolds D is less than Reynolds D critical, therefore, which would be equal to 2,300, and therefore we have laminar flow is okay. So we can say that our assumption was safe to do laminar flow. So let's recap this problem a little bit. So we started off this problem saying that we had to verify if the velocity was up and finding HF. In order to find HF, you cannot directly use the equation for HF given here. You can't use HF is equal to 128 mu LQ over pi rho g d to the fourth. The reason why is because you don't have Q. So you need to find HF another way. How do we find HF? We can find HF directly from an energy analysis of our pipe. So we use an energy analysis of our pipe to verify that the flow is up and also compute HF. Once we have HF, we can use the equation for HF to find Q, V, and Reynolds at the end can be found with the velocity of our flow. So that's just one example. There's another example in your book, which is example 6.4. It is in US units, but it is also interesting to do. And in live lecture 4, we are going to be looking at turbulent flows because turbulent flows are a little bit more complicated. And we will be looking at the theory of turbulent flows. and looking at how we can apply them to problems using uh, kind of a special technique using Moody charts. Okay, so we'll see you in live lecture 4 to discuss turbulence next time.